Welcome back everyone. In this lecture, we will focus on symmetric and alternating groups and then prove some of their basic properties. So first let's recall what is symmetric group. So symmetric group is the permutation group on this n letters 1 to n. Okay. So recall. So the symmetric group by definition it is the permutation group on this 1 to n. So we have already seen that the cardinality of this Sn is actually n factorial. So we have used many different notation to denote the elements of the symmetric group. So we will actually stick with the following notation throughout this lecture. So we already proved some important results about the symmetric group. So one of the main result is the Cayley's theorem. So what it states, let me recall the statement. So here is the Cayley's theorem. So what it says, if you start with a finite group of order n, okay, so then it is isomorphic to a subgroup of Sn. So that's what it says. So any finite group of order n is isomorphic to a subgroup of Sn. So this shows importance of this symmetric groups. So understanding the symmetric group and its subgroups amounts to actually from the Cayley's theorem amounts to saying that it is actually to understand all finite groups, it is enough to understand all subgroups of Sn. But anyway, the classification problem is not that easy. Classifying all subgroups of Sn is not some easy problem. So let us now work with symmetric group and then try to prove some of its basic properties. So first let's fix some notation. So if you start with an element sigma of Sn, okay, so we can use this notation In to denote this 1 to n. So then you take some element sigma, so which is a permutation of this 1 to n. So in particularly it is a bijective map from In to In. So this is a bijective map. So in order to actually note down what this sigma does to this 1 to n, it is actually enough to understand image of each I. So we can use this shorthand notation to write down the same map as follows. You write the domain on the top 1 to n and then you write the image sigma of 1, sigma of 2 at the bottom. Okay. So this is the shorthand notation that we were using before. Okay. We can also use this one line notation. Okay. So we can also write sigma as sigma 1, sigma 2, etc., sigma n. So this is called one line notation or word notation, but this is something we are not going to use in this lecture. So we will stick with this particular notation. So now recall that what is a cycle of length R. So it is a very specific element of the symmetric group. Actually it permutes some particular indices in cyclically. So let us define it properly. So here is the definition. So we want to define what is called cycle of length k. So cycle of length k by definition it should permute k many number of indices cyclically. So you start with some, okay, so you start with some sigma which is in Sn. So this is called a cycle of length k if it permutes some k distinct indices cyclically. So what does it mean? So if there exist distinct indices, so distinct elements, okay, a1 etc. ak, from this In such that if you apply sigma on A1 then you get A2, and then you apply sigma on A2 you get A3 and so on. Then when you apply sigma on AK you get back A1. So, this should be true. Okay. And if you take any other I outside this A1 etc. AK, then that should be fixed for any I which is not coming from A1 etc. AK. So, that means it just cyclically permutes. So, using this pictorial definition you can see that. So, sigma actually maps A1 to A2 and then A2 to A3 and so on. Then finally, it reaches AK and then AK is mapped to A1 under this sigma. Okay. And it fixes all other elements I which is not from A1 etc. AK. So, if sigma actually satisfies this property, then we denote sigma as follows. Sigma is denoted using this parenthesis notation, parenthesis A1, A2 etc. AK. So, note that we do not put comma in between these indices. So, this is the notation for the cycle of length k, which is defined as above. Okay. So, now what is transposition? So, recall that transposition is nothing but cycle of length 2. Okay. So, here is the definition: a cycle of length 2 is called transposition. Okay. So, now why these things are important? So, we are going to prove one important structure theorem for permutations. Okay. So, which states that if you take any permutation sigma of Sn, then that can be written as product of disjoint cycles. Okay. So, in particularly if you understand what happens, how to multiply these disjoint cycles, then you understand everything about permutations. Okay. So, let me just do an example and then later we will actually prove that result. So, for cycle, let us see the following example. So, you start with this sigma, so which is let us say 1, 2, 3, 4, 5 from S5. So, where 1 map to 1, 2 map to 4, 3 map to 2, 4 map to 5 and 5 map to 3. So, then if you think about it, then you can see that 1 is mapped to 1. So, it is not actually does anything on 1, but if you take all other indices, so then what it does, it actually permutes them cyclically. So, you can see that 2 is mapped to 4 and then 4 is mapped to 5 and 5 is mapped to 3 and then 3 mapped to 2. Okay. So, in particularly this sigma is nothing but a cycle of length 4, 2, 4, 5, 3. Okay. So, this is one example of a cycle in S5. So, now it is not hard to see because sigma actually permutes this A1 etc. AK cyclically. So, if you think about it, if you take a cycle of length k, if you denote it by A1, A2 etc. AK. So, using the same cycle notation you can see that this is same as A2, A3 etc. AK, A1, and you can actually cyclically permute them and then you can see that this is same as A3 etc. AK, A1, A2 and so on. Then finally, you can reach to AK, A1 etc. AK minus 1. So, all these cyclically permuted okay, cyclic permutations, you start with this particular one and then you obtain all other cyclic permutation by cyclically permuting those indices, then we will be getting the same sigma. So, we do not change it. Okay. So, that is very clear from the definition. So, So, using this notation we can see that this must be true. So, now what we are going to do, we want to talk about this cyclic decomposition of a given permutation. So, for that we need to first understand when given two permutation called disjoint. Okay. So, what is the meaning of disjoint? Okay. So, you look at the permutation. So, the permutation fixes certain points. Okay. So, those points are not important. So, permutation indeed read from those indices that are actually really permuted by sigma. Okay. If it is fixed, then it does not do anything on that particular fixed point subset. So, in particularly if you want to call sigma tau, they are elements in Sn. So, they are said to be disjoint. So, they are disjoint if you look at all those indices that are not fixed by sigma, those I in In such that sigma phi is not equal to I. So, this set should be disjoint from those j in In such that which is not fixed by tau. Okay. So, this should be disjoint. Okay. So, what is the meaning of that? So, if you think about it, a permutation sigma is actually somewhat uniquely determined by the action of sigma on this set, those indices which are not fixed by sigma. Similarly, tau is also determined by the action of tau on this particular set, those indices which are not fixed by tau. So, now what we want to say, sigma and tau they are disjoint, so they do not have anything in common. That means these two sets must be disjoint. Okay. So, that the action of sigma is very different from the action of tau. Okay. So, now once we understand the definition, it is not hard to prove the following proposition. Okay. So, I will leave it as exercise. If sigma and tau are disjoint, then they must commute. Okay. If sigma tau, if they are disjoint, so then if you just take this product sigma tau, that should be same as tau sigma. So, why it is the case? Because you just compute the action of sigma tau on some given index I. Okay. Then you can see that this I, if it is not coming from these two sets which are there in this. So, then it has to be fixed by both sigma and tau. So, then the action on both sides sigma tau and tau sigma will be same. And if it is coming from one of them, you can see that since sigma is determined by this particular set. So, this particular set, if this I comes from this set, then tau does not do anything to that. Okay. So, let me just write down the proof, because the proof is not that hard. Suppose I is not coming from, let us say call this set is A sigma and then this set is A tau. Okay. So, if this I, so let me call using different notation. Let us take this A, which is not from A sigma union A tau. So, then you can see that sigma of A will be A and tau of A will be A. So, in particularly sigma tau of A will be exactly A and as well as tau of sigma of A. Okay. So, now if this A comes from this A sigma, so then what happens? So, because A sigma is disjoint from A tau, you can see that tau of sigma should be tau of A should be A. In particularly sigma tau of A is going to be sigma of A, and similarly tau of sigma of A is going to be tau of So, if sigma is actually A is coming from A sigma, so then we have to see what it means. So, it means sigma of A is not equal to A. In particularly, A is also not equal to sigma inverse of A. Okay. So, since sigma of A is not equal to A, you can see that this tau, the sigma of A also cannot be inside. Okay. So, let us see. So, what we need to say? We need to say that tau actually fixes the sigma of A. So, it is enough to see that sigma of A cannot be inside this A tau. Okay. So, because A tau A tau is nothing but those indices j such that those indices inside in such that tau of j is not equal to j. Okay. So, if we can say that sigma of A cannot be actually fixed by this tau of by tau, then we are done. Okay. So, since sigma of A is not equal to A, and you can see that sigma of A is going to be either fixed or not fixed. Okay. But anyway, so what we need to say, so note that sigma of A is actually not equal to A. So, in case tau of sigma of A is not equal to sigma of A, then that would imply that sigma of A is actually inside this A tau. Okay. Because A tau is defined to be those indices j such that tau of j is not equal to j. So, since A tau and A sigma they are all disjoint, okay, you can see that this forces that sigma of A, if when you apply sigma on this, that should be exactly equal to sigma of A. So, this would say that sigma of A is not in A sigma. So, that means sigma when you apply on sigma of A, then that should fix sigma of A. But now you can apply sigma inverse on both sides. So, applying sigma inverse, so we get sigma of A equal to A. You apply sigma inverse on this, then you get sigma of A equal to A, which is a contradiction. So, that forces that tau of sigma of A must be exactly equal to sigma of A. So, that is what we wanted to prove. One hand we have sigma tau of A equal to sigma of A, on the other hand we have tau of sigma of A equal to sigma of A. So, this says that sigma tau of A is same as tau of sigma of A. So, now we have chosen A from A sigma. Similar argument will hold for if you choose A from A tau. Okay. So, that actually completes the proof. So, basically the action of sigma determined on this A sigma. Similarly, the action of tau is determined on this A tau. If they are disjoint, then when you compose them, they do not actually interact with each other. So, they must commute. So, that is what this proposition says. Okay. So, now we are ready to state our main result. Okay. So, let us take any permutation sigma in Sn. So, here is the theorem. So, for any sigma in Sn, so there exist unique cycles tau 1 etc. tau k such that, so they are all disjoint cycles. Okay. So, given sigma in Sn, there exists unique, let us call it tau 1 etc. tau k. So, the order is not important. So, I can put this collection tau 1 etc. tau k of disjoint cycles such that the sigma can be written as the product tau 1 etc. tau k. So since they are all disjoint cycles, the order in which you take this product, that doesn't matter, okay, because for any permutation, so you can actually permute of 1 to k, you can permute this tau 1 etc. tau k and then take the product of them. So that will be still equal to sigma. So this, because of this disjoint, so we are allowed to permute this tau 1 etc. tau k. So let us see how one can actually prove this theorem. So before actually proving this theorem, let us see one example. So more or less the example actually tells us what to do with this result. So let us consider this particular sigma which is coming from S9. Okay, so take 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is from S9. So let us say 1 goes to 4, 2 goes to 7, 3 goes to 1 and 4 goes to 3, 5 goes to 2, 6, 5, 9, 8. So now what we want to do, we want to actually write this sigma as product of disjoint cycles. So then if in case if you are able to write given permutation as product of disjoint cycles, you can see that each cycle that appears in that decomposition, so they don't interact with each other, okay. And if you think about it, okay, if you fix one cycle and then look at its action on given some element in that cycle, okay, some index in that cycle, so that cycle is indeed takes, okay, all other elements in that cycle can be obtained by applying that cycle repeatedly on that particular index, okay. So let me just state what I'm trying to say. If you write sigma as, let us say, tau 1 etc. tau k, and tau 1 is nothing but some a1 etc. ar, then you can see that this tau 1 tau 2 they will not have anything in common, okay. In case if you want to get tau 1, then what you need to do, you can pick a1 and then you can repeatedly apply this tau 1 on this a1. So then a2 will be obtained by tau of a1 and so on. Then ar will be just tau of ar minus 1, which is same as tau r minus 1 on tau 1 r minus 1 on a1. So what I am saying, so you start with this a1, repeatedly apply this tau 1 on this a1, then you obtain all other elements that appear in tau 1, okay. So that way you can reconstruct this tau 1. But if you think about it, this tau 1 is nothing but a1 tau 1 a1 etc. tau r minus 1 a1, tau 1 r minus 1 a1. But indeed, since sigma is actually product of this tau 1 etc. tau k, so then it says that this tau 1 restricted on this a1 tau 1 a1 etc. tau 1 power r minus 1 a1. So this should be same as sigma restricted on this set a1 etc. this ak. So this means if you are interested in writing this tau 1 in terms of sigma, then you can see that this is same as you start with a1, you apply sigma on a1 and so on. So you repeatedly apply this sigma on a1, then you get back all other elements, okay. So this tells us that in case if you are able to write sigma as product of disjoint cycles, then if you want to recover tau 1, then this is the way to recover. You pick one index that appear in that cycle, then you repeatedly apply sigma, then you get back all the other elements from that cycle. Similarly, if you go to tau 2, then what happens? You pick one index in tau 2 and you repeatedly apply sigma, then you get back tau 2. So this is the way you get all tau 1 etc. tau k, okay. So this algorithm works for general permutation in general symmetric group, okay. So let us try to do this for this particular example. So this sigma, so you can start with any index, okay. For example, I can start with 1. So, then you see where this 1 goes. So, you can see that. So, this 1 goes to 4 and 4 goes to 3 and 3 goes to 1. So, then if I want to write down this cyclic decomposition, then you can see that I can start with this 1 and then go to this image 4, which is sigma of 1, then go to its image under sigma, which is 3, sigma of 4 is 3, then sigma of 3 is 1. So, then this cycle is closed. So, now you have made one cycle. Now, if you want to go to the next cycle, so because all of them are disjoint, so which cycle you choose first does not matter. Okay? That means which index that you choose does not matter. So, you can now go to some index which is not presented in this first cycle. Okay? For example, what I can do, I can go to 2 and then I can start playing this similar game. So, you can see that 2 is mapped to 7, 7 is mapped to 5 and 5 is mapped to 2 again. So, then the second cycle will be you take 2 and then it mapped to 5, sorry, 2 mapped to 7, 7 mapped to 5 and then 5 mapped to 2. So, this cycle closes. So, now what you can do, you can take some index which is not in both of them and then you can actually start playing the same game. For example, 6 goes to 6, so there is nothing to write, you can write just 6 here. And then if you go to the next one, so let us take 8, then 8 goes to 9 and then 9 goes to 8. Then this will give you 8, 9. So, this is your cyclic decomposition of sigma into product of disjoint cycles. So, now if you want to double check whether what you did is correct or not, you can see that if you want to actually just calculate what is on the right side. Okay, this is something like product of cycles. You can see that, for example, what will be the image of 8. So, the 8 goes to 9, but 9 in this particular cycle it is fixed. So, 9 is fixed again here, fixed again here. So, that means in this product 9 actually goes to 8. So, 9 only goes to 8. Similarly, this 8 actually goes to 9 and then 9 is fixed. So, 8 goes to 9. So, 8 goes to 9 and 9 goes to 8, that is all happens here, because in all other places 8 goes to 8, 9 goes to 9. So, because of that you can see that the only effect that will have, okay, that is on 8 or 9, that comes from this particular cycle at the end. Okay. So, this proves that you can actually write down this cyclic decomposition by looking at some particular images of some indices. Okay. So, how to make this more rigorous? So, already we have seen that this is what we should do, okay, from this cyclic decomposition. So, let us do it rigorously. Okay. So, to do this rigorously, what we need to do, we need to define an equivalence relation on this 1 to n. So, define the following relation, define a relation, call it tilde sigma on this in. So, which is 1 to n. Okay. So, how it is defined? So, this is defined as follows. So, for I comma j comes from in, we say I is related under sigma, okay, tilde sigma, I and j are related under tilde sigma if and only if there exists k in z such that sigma k power I equal to j. So, we want to say that by applying some higher power of sigma on I, you will get j. So, note that we are in the group, okay, finite group. So, sigma inverse is going to be some power of sigma. So, even though we have allowed k to vary over integers, so indeed it will vary only from 0 to infinity, okay, and it will not vary over up to infinity. So, because we are in the finite group, it can vary over up to order of sigma. Okay. But anyway, it's comfortable to actually define this way. So, now once you have defined this, you can check that this is indeed equivalence relation. So, tilde sigma is on equivalence relation. So, how do we check? So, we need to check three things. So, first it is reflexive. Okay. So, first you can see that. So, I is related to I. So, by taking k equal to 0. So, sigma power 0 you can identify with identity. So, that is obvious. The second thing is, if I is related to j, then you can see that if and only if there exists k inside integer such that sigma power k I equal to j. So, now by applying sigma power minus k, you can see that sigma power minus k on j is going to be I. So, then if and only if you can see that j is related to I. So, now what is the third condition? So, this is symmetric, reflexive, they are done. So, now the transitive condition, if I is related to j and j is related to k, so then we want to say that I is related to k. So, note that if I is related to j, then we have some k such that sigma power k of I equal to j for some k in z. Similarly, sigma power k dash of j will be k again for some k dash in z. So, now from this you can easily see that sigma power k dash plus k on I is going to be sigma k dash of sigma k I, which is going to be sigma k dash of j. So, which is going to be k. Okay, maybe I should use some other index. So, maybe this I will call it R. So, this is j is related to R and sigma of k dash of j is R, and then this is going to be R. So, that shows that this I is related to R by this tilde sigma. So, this proves that this relation that we have defined tilde sigma is indeed equivalence relation. So, once we know that this is an equivalence relation, then you can easily see that the set In can be decomposed into disjoint union of equivalence classes. Okay. Now, look at some particular equivalence class and then see what it is. Okay. I will leave it to you to verify, this is not very hard. If you fix some I in this In, then this equivalence class related to I, okay, with respect to sigma tilde sigma. So, this is going to be just sigma power k of I, where k ranges over integers. It is basically you apply sigma on I repeatedly. So, then whatever indices that you get, so that will be your equivalence class. Okay. So, this is also same as you take I, you apply sigma on I and so on, and you go along like this. Okay. So, this is going to be exactly your equivalence class. So, now from this we can easily see that this In can be written as disjoint union of these equivalence classes. Okay. So, this you call it orbit of I, because you are looking at the action of sigma on I and then you are taking repeated action of sigma on I. So, that is called the orbit of I. Okay. So, this we can call it orbit of I. So, all these things are related to group actions, which we will see later. Okay. But anyway, this we are talking about a particular group action here. Okay. So, later when we come to group action, it will become clear what group we are talking about and which group is acting on which. So, anyway, so this I will now vary over some indexing set capital lambda. What is this capital lambda? So, capital lambda chosen to be a subset of In, which is the indexing set for each orbit. So, you choose capital lambda from In such that whenever you take lambda intersection with some orbit, so this has to be exactly singleton for each orbit OI. Okay. So, it is a indexing set chosen from In such that lambda intersection OI is exactly 1. So, basically what we have done, we have partitioned this In into smaller subsets. Okay. So, these are all some orbits OI. So, then in this OI what you do, you collect one element I. So, then you form this capital lambda. So, capital lambda is just chosen something from this each orbit and then you collect them together and form a set. So, that is called this indexing set of these orbits. So, now it is very clear that this In is just a disjoint union of all these orbits. Okay. So, now if you go back to your sigma, you want to write this sigma as product of disjoint cycles. So, then it is clear that what this sigma does to each orbit. So, it is easy to see the sigma maps the orbit to orbit. Okay. Because by definition of this orbit, you can see that. So, you have fixed this I, you have repeatedly applied sigma on that I. So, that implies that the sigma just leaves this orbit invariant, and any invariant subset, okay, of this In under sigma will be union of these orbits. Okay. So, any S of In such that sigma of S equal to S. So, this maybe you can take it as exercise is union of some orbits OI. Okay. So, any invariant subset, sigma invariant subset is going to be union of some orbits. So, these are all the important properties. Now, you can see that. So, once you have realized this, so then because OI is going to be subset of In is finite. So, OI can be actually listed as some A1 etc. AK. Now, if you think about it, that A1 etc. AK can be obtained from A1 by repeatedly applying this sigma. Okay. So, if you denote this by A1 etc. AK, where these AIs are all distinct. So, then you can see that there is a natural permutation that is associated with this Y. So, what you do? You define this sigma I, okay, as follows. So, define sigma I from this In to In such that, so what is, how it is defined? So, it is exactly defined the way it acts on this orbit. Okay. So, sigma I is going to be restricted, sigma I restricted to OI is going to be sigma, and sigma I on all other elements is going to be identity on this In difference OI. So, you just take sigma I to be sigma on OI, and then you take it is identity on all other elements. Okay. So, if you think about it, what it does, so sigma I of A is going to be sigma of A if A comes from this Y, and it is going to be identity if B is not coming from this Y. Okay. So, then it is clear that the sigma I is nothing but permutation on 1 to n. Okay. So, this is indeed a permutation. Not only that, the sigma I is indeed a cycle of length k. Okay. So, sigma I is this A1 etc. AK, where this A1 etc. AK fixed as follows, where this OI is given to be A1, where A2 is sigma of A1 and then A3 is sigma of A2 and so on, then AK is sigma of AK minus 1. Okay. And the cardinality of this OI is nothing but K. So, basically the sigma I just permutes all the elements in that orbit, and since sigma I is nothing but sigma, so they just coincide with the same action. So, now all these orbits are disjoint. So, that actually simply says that all these sigma i's are mutually commuting. The sigma i's, where I range from, let us say there are r orbits. Okay. So, let us say O1 etc. OR, maybe let us call it OI1 etc. OIR, or the distinct orbits or disjoint orbits of IM. Okay. So, that R is going to be nothing but the cardinality of lambda. So, now you can see that, so these are all mutually commuting cycles. Why? Because they are all, they corresponds to, their support actually corresponds to disjoint orbits. Okay. So, now it is easy to see sigma has to be just product of these sigma 1 etc. sigma. Okay. So, I will leave it to you to verify all of this. So, this is like once you have constructed what is the sigma I, then it is not hard to prove that the sigma is actually just product of the sigma 1 etc. sigma. Now, so once we understand this, then from the definition it is very clear that the sigma I is actually associated with this orbits. So, orbits uniquely determines the sigma I. So, because of that, the uniqueness of the sigma I or the cyclic decomposition also becomes clear. Okay. So, again verify the uniqueness of this cyclic decomposition. So, all you need to actually check sigma I actually corresponds to OI. Okay. And this I is now coming from this capital lambda. So, more or less it is clear once you know this decomposition into orbits. These orbits are very explicitly given by, for example, if it is coming from I, then this is going to be I sigma I and so on. Okay. Because of that, so what you are doing, you are defining the sigma I, which is just restricted, sigma restricted to OI on this, all other elements are fixed. So, from that you are reconstructing sigma as product of the sigma i's. Okay. So, this is more or less clear from the definition of sigma i's. So, now the uniqueness is very clear because sigma I corresponds to these orbits OI. So, this proves that any given permutation can be written as a product of disjoint cycles. So, now since these disjoint cycles, so they are all like uniquely determined by sigma. So, you can see that if you take the sign of this sigma, you can see that that will be just product of the sign of each sigma I. Okay. So, we already have this sign map, recall that the sign map is a map from Sn to this plus or minus 1. So, now you can see that if sigma is in the kernel of this sign map, so which we denoted by AN, the alternating group, if and only if the sign of this sigma must be equal to 1. So, that means if and only if you write sigma as the product of sigma 1 etc. sigma r, where this is the cyclic decomposition of sigma, then you can see that the sign of this sigma is going to be exactly the sign of sigma 1 product etc. sign of sigma r. But what will be the sign of sigma 1? Okay. So, I will leave it as exercise. Sign of any cyclic permutation, if you write let us say tau, which is a cyclic permutation A1 etc. AK. So, then the sign of this tau is exactly going to be minus 1 power k plus 1. So, in particularly, so this is going to be the sign of sigma is going to be minus 1 power the length of this cycle sigma 1. So, the k is called the length of this tau, okay, plus etc. plus length of this sigma r plus r. So, then if you keep this aside, you can see that. So, this sign of sigma is 1 if and only if you can see that the length of cycle sigma 1 etc. plus length of this sigma r plus r, that is supposed to be even number. Okay. So, now if it is actually a product of so the sum of the length, that should be even, that is what it says. So, product, if you write it as product of disjoint cycles, then if you count the length of each cycle and add it, then that should be congruent to 0 modulo 2. So, this is one of the characterization for sigma being a. So, we will actually use this kind of characterization later, and then we will understand more about this group, alternating group A. Okay. I will stop now here. We will actually continue with some more basic properties in the next lecture. Thank you.